Hey everybody, this is Larry. This is me going over Q4 of the recent Leetcode bi-weekly contest 39. Wow, I'm just taking a notice that it's a 6-pointer, but that was kind of hard. And a lot of people kind of took their time with it, like the top people. So I think they kind of the points don't really matter as I try to finish all of them anyway. But I would say this is a harder than normal 6, so don't feel bad about it. But yeah, so look at the code first. So yeah, so this problem is called distribute repeating integers. So this is a really tricky problem, and I think this is a problem where you try to do the best you can with identifying states. And the first thing I would do is that just make sure you look at the constraints. So my when I first look at this, and some of this is from experience during the contest, is that when I read this problem, I was like, this is too hard to be greedy. When I say hard, I mean in the computational sense. And this is something that when you do enough competitive programming problems, you'll recognize these patterns where you know that if it's greedy, it has to be something weird about it that gives it greedy true. Otherwise, it's like some sort of variation of NP, right? Like you have to do exhaustive search or exponential time stuff. So I took a look at the constraints, the first thing I do after that, and there are two key things to notice. One is that there are at most 50 unique values in nums, and the other is that m is equal to 10, which is the quantity that you have to fill. So immediately, that gives me a hint that it has to be dynamic programming. The fact that m is equal to 10 gives me a hint that I can kind of, think about how to handle it. And for me, with these kind of problems, what I would try to do is try to impose a structure to the problems in a way such that you when you go left to right on a suffix or something like that, you don't have to go back, and there's no need to go back, or going back does not give you a better answer because you've already answered it. And for me, the m is equal to 10 was the biggest clue. And I'm going to explain my states, but I'm just right now explaining my thought process. Hopefully that's more interesting. If not, fast forward, I'll explain the solution, no worries. Watch it on 2x. But yeah, so the idea here is that, well, because there are only 50 unique nums, this nums array, even though it has 10 to the 5th elements, this nums array is essentially, an array of 50 elements, just like a collections of counter, right? Which is what I do here. Basically, you could just compress it into an array of 50 elements, and that'll be good enough. And now basically what you have is 50 elements that you cannot, or actually that you can divide, and then you have to have some, summation things there from quantity, right? I know I'm hand waving a bit, but that's how I thought at the time. And the next thing I thought was, okay, can it be some kind of knapsack, right? Like, but then just working it out, but I was like, okay, that's going to be too, given that each number in this collection stat counter can be up to 10 to the 5th, or like something smaller, say, but, knapsack was going to, like the range of numbers is too big. Maybe you could do it. I couldn't really figure out how to make the numbers work for sure. So I didn't do it that way. Or I might have pursued it if I had no other choice, but I was thinking about another way. And then the thing that I took notice again is that m is less than 10, so we can really brute force on 10, right? And the idea now then is that we have a bit mask of, okay, you have 10 elements, so because 10 is small enough, you could do some 2 to the 10 things, like 10 to the 24, 2 to the 10, which is 1024, and you could do some bit mask thing there. And from that, I thought about the idea and go, okay, that means that we have 10 items, and we either satisfy some subset of the 10 items, and we want to satisfy all 10 items. So, and there's only 10, again, 2 to the 10 possibilities, so that's going to be an index. And on the left side, we have this counter thing. So we just have to kind of implement it in a way so that the transition going from left to right, once we used a number, a column, I call it a bucket or something, because this is just, I count these as buckets of numbers, but once we use the bucket, we could throw it away, right? So basically, that's how I grew this up. I actually also wrote a cache that just sums up the things, which I'll explain in a second. So that's basically my states. Index is and if you kind of follow through, there are a couple of steps to each of these. So that's what makes this hard, is that it's not straightforward. Is that there are a lot of like little problems that you have to solve to get to this state. And so index is actually, like, for example, to document this code, CV is just the number of, I'm going to just say balls in a bucket. And this is just the implementation of it, right? I'm going to explain the cache part later. So index is what current number bucket we're on. We already considered all buckets to the left of index. And mask is just a bit mask of all the quantities that we already filled, right? And in this case, I count from 1 to 0 to make certain math a little bit easier. So for example, if this bit mask is this, that means that all quantities need to be filled. So I would say right now, a prerequisite for understanding this part does require bit mask. I have a video that I'll put in a link below so that you could kind of learn more about bit masks in general and how to use them to solve this problem. But I'm not going to explain it here because I want to keep this video short. But you know, I'll give you the tools. But assuming that you already know how a bit mask works, so yeah. But just to kind of give a 20-second overview. So if you have something like this, that means that first quantity needs to be filled, or it's first, second, fourth, and sixth, because we have ones in the first position, second position, fourth position, and the sixth position, right? You know, you could do some math about lowest significant bit versus most significant bit, but that's a general idea. And then now we could go through our states, right? If mask is 0, that means that if all our quantities are filled, we could return true, because that means that there is a path to get there. We can, you know, that means that we can actually return true. If the index is equal to m, that means we already used all the buckets, and that means that it's no good. No good, because we already used all the buckets and mask is not 0. That means that, you know, there's still mask to be filled, but m is equal, or index is true. And m, of course, is just the number of buckets we have. And then this part is just going through all the possibilities. And this is a little bit advanced technique, though there's though I think, and I'm just thinking about what would Alex do as a Python person, because this is a little bit more C. You could actually use iter tools and combinations to kind of do the subset of your bit mask. So basically that's what this does, is that this gets me the subset of the bit mask so that we don't have to count it. This is a little bit magic. I'm not going to explain it again. I'll put a link below on the explanations, but basically this just lets me get all the subset of the bit mask, so that, for example, if we have this bit mask here, then this goes through 1 0 0 0 0 0, it does 1 1 0 0 0 0 0, it does 0 1 0 0 0 0, and basically all the subsets of this thing, and the key thing to note is that because we don't iterate over either of the zeros in these in the original bit mask, this allows us to be faster. And the key thing to note for that is that as a result, and the math is a little bit tricky, I'm a little bit hand waving, I'm not going to prove this, but it drops our complexity from 4 to the n to O of 3 to the n. And I'm going to go over it in a little bit, but that's why I kind of write this in a funky way, because I was trying to be a little bit, make sure that I'm a little bit faster. Anyway, yeah. And then the recurrence is, okay, we have, so given that we have, let's say we want to fill the first, second, fourth, and the sixth, right? Well, what are the criteria to fill this? Well, the criteria to fill this then is that if the quantity of these four, the sum of these 4 buckets is less than the number of balls in the bucket, then we can, mark them as being off, right? So that's basically it. But I knew that if I do a for loop to do the summing, it's going to take a little bit long. So I actually preemptively, for all combinations, do the sum here. So that's basically what this does. I'm not going to go into too much, but you can kind of see that, and this requires some understanding of bit masks as well, but you can basically see that for each bit mask combination, for example, for this one, we just do a for loop so that it looks at all these numbers, it sums it up to this total amount for a given bit mask, given the quantity number. So that's basically what I have here. And basically here, I just retrieve it instead of doing another for loop so that it makes it faster. And yeah, oops. And as long, and if this condition is true, meaning that if the number of balls that we have in this bucket is fewer than the bit mask that we're satisfying, then we could check the recursively the rest of the constraints, which is that we use this bucket, so it's index plus 1, and then we use this bit mask XOR to check off the things that we're using now. So now, for example, in this case, let's say we use the first, second, and the fourth and the sixth bucket. Then in this case, mask XOR sub I will give you 0, 0, 1, 0, 0, 1. So that means that now your recursion will be, okay, now the third and the fifth needs to be filled. So that's basically the recurrence, and it's pretty straightforward once you have all the foundations. And again, there are a lot of foundations that you need to understand before this can be solved this way. So if you're having trouble understanding my explanation, I would advocate practicing bit mask problems, that's 1, and also practicing bit mask dynamic programming problems, that's 2. And then this will become a little bit easier, because then you're able to do these optimizations. And if you look at it that way, if you look at how I describe the problem, I actually solve like 4 different problems almost, right, kind of thing. And that's why this is hard, right? Like first, I have to put the balls in a bucket so that it's faster. And then now I do this caching so that the caching is faster, right? And then I have to do this bitmask DP on these things, and also, constructing this problem in a way so that you can understand. And putting it all together is not easy. You have to be really strong at each step of the way so that when you're solving this, when you notice these things, you're able to go through it directly. So the explanation so that's all I have for this explanation. I'm going to go over the time complexity here. So this for loop is clearly n times 2 to the n. So this is going to be O of n times 2 to the n. In this case, it's a little bit tricky to explain this. And it's actually easier if I do this bottoms up dynamic programming. But basically you have O of m state so index can be obviously 0 to m, so that's O of m number of states. Mask can go from 0 to 2 to the n, so this is O of 2 to the n states. So a naive interpretation of this is that, and this is for each state, okay, so total number of states is equal to O of m times 2 to the n. And for each state does this amount of work. And what is this? Let's just say it's 2 to the n for now. So naive analysis of this is going to be m times 2 to the n times 2 to the n, and that is actually not fast. I actually don't know if this is fast enough, but I actually think it's a little bit too slow. But it turns out because of the way that I did this bit mask thing, where it only counts the bit mask. If you do the math, and there are videos on that will explain this derivation, but it turns out to be m times 3 to the n, which for m is equal to 50 times 3 to the 10 times 50. It's actually only so for m is equal to 50 and n is equal to 10. This is roughly equal to 3 million. So this is fast enough for that reason. And this is only with these optimizations that this is fast enough, in my opinion, right? So that makes it really tough because, well, maybe in C++, another language, maybe it's fast enough. But in Python, this is the case for me, intuitively. Because without this, it's a little bit yucky. And for example, this loop, if we have to do another for loop, well, this is going to times this loop by another n, and another n is another 10, right? So that's going to be 10. It's going to be 30 million, which is usually too slow in Python. So that's why I had to do this lookup table. But yeah, whew. And in terms of space, well, we have this amount of states, so that's going to be your worst case number of states, or it's actually, I guess, n times 2 to the n plus m times 2 to the m. So your space is just equal to this times 2 to the n. It's a long explanation because it's a long problem. I hope that was understandable. Let me know what you think. Let me know if you still have any questions. And you could watch me solve it live during the contest next. I should have done that. Really dumb. Rushed it. Quantity is 10. think I know how to solve this, but I'm not sure. Well, people got it. That's great. Okay. Yeah, we'll see. I think this is okay. Return true. Come on. Okay. So stupid on. Hey, thanks for watching. Hit the like button, hit the subscribe button, join me on Discord. Let me know if you have any more questions about this problem or another problem. I will see y'all next problem. Bye bye.